and I am going to give you the online lessons on quantum mechanics for this semester. You have already gone through the basics of the quantum mechanics and application of the quantum mechanical principles for simple systems such as particle in a one-dimensional box, particle in a three-dimensional box, and you have applied various boundary conditions, and you have found how the results are changing when the boundary conditions are changing, and you are already familiar with applying the Schrodinger wave equation for the simple systems. And in this semester we have to extend our studies on quantum mechanics to other systems as well, and now we will learn a simple system, and this simple system is particle in a ring. Particle in a ring. In a ring. And before proceeding to the particle in a ring system, you have to have some basic understanding of the polar coordinates. I know that you are all familiar with the Cartesian coordinates x, y, z, but since we are going to deal with a circular motion, and it is convenient to use the polar coordinates, we will get the more convenient results, the results which are more easy to look into if we are using the polar coordinates. So we will switch our study of the Schrodinger wave equation for the system to polar coordinates. You can use the Cartesian coordinates as well. You will of course get the results, but it is easier to use the polar coordinates this time. So you should have some basic understanding of this. Many of you may have understanding of the polar coordinates as you have studied mathematics and physics in your lower classes, but I just want to remind you what the polar coordinate is. And I'm not going to the details of that because I guess that most of you are already familiar with that, and I will give only a short reminder of what you have already learned in your lower classes. So these polar coordinates, we are going to specify three coordinates, that is, or three parameters: r, theta, and phi. And I will explain what are these r, theta, and phi. Suppose you want to locate a point in the space. You want to locate a point in the space. In order to locate the point in the space, you first set up a coordinate system. Let us have an z-axis here. This is the z-axis, and we have an x-axis here, and perpendicular to that we have the y-axis. Here we have the y-axis as well. And in Cartesian coordinates it is easy to, you are already familiar how we are going to locate a point. You have to specify the x, y, and z. X, y, z. For example, if x, y, z is 3, 2, 4, it means that you have to travel 3 units in the x direction, then you have to travel 2 units in the y direction, and then you have to travel 4 units in the z direction, and at the end you will reach that point. So if you have x, y, z coordinates, you know how to locate that point in space. Here in the case of the polar coordinates, we are using r, theta, and phi. Now I will explain what are these r, theta, and phi. Suppose you want to locate a point in space, and instead of saying x, y, and z coordinates, you are going to tell how far is that point from the origin of the coordinate system. The origin of the coordinate system is here. This is the origin of the coordinate system. And you are going to say how far is this point from the origin of the coordinate system. Let's say that it is at a distance of r from the coordinate system. So r is the distance of the point that we have to locate from the origin of the coordinate system. So let that point be somewhere here. This is the point, Suppose you just pretend that we already know that point even before giving the coordinates, and this is the point that we have to locate. So we say that it is at a distance of r from the origin. See, this is r. This is at a distance of r from the origin. So is this enough to locate that point? No, because there are infinite number of points at a distance of r from this origin, right? Not only this point. If you are looking at this point, this is also a distance of r. If you are looking at this point, this is also a distance of r. This one is also a distance of r. So there are infinite number of points which are placed at a distance r from the origin of the coordinate system. So if you are looking at all these points, you can say that these are the points on the surface of a sphere. These are the points on the surface of a sphere. So we have a sphere here, and all the points on the surface of this sphere will be at a distance of r from the coordinate system. So specifying only r is not enough to locate that point. R is a good thing to know where the point is. At least now we know that this is somewhere on the surface of the sphere, but that is not enough to locate that point. We have to go closer to that point, right? So in order to go closer to that point, what we are going to say next is, what is the angle of r? R is actually a vector. That vector is from the origin of the coordinate system to the point to be located, right? And we are going to say, what is the angle of this r from the z axis? We are saying the angle from the positive z axis, that is from here. This is a positive side, this is a positive side of the z axis, and this is a negative side of the z axis. And we are going to say, what is the angle from the z axis, that is a positive side of the z axis, to the r? See, this is that angle. We are going to specify what is that angle, and that angle is theta. That angle is theta. This is theta. So we are going to say one more parameter, that is theta. So if we say theta, then we don't need to go over the entire surface of the sphere, because once we specify theta, the number of points satisfying r and theta conditions will be limited on the surface of the sphere. You know that this point is at this. If this is the point, then r will be at an angle of theta, and if this is the point that you are looking for, this is also at an angle of theta, right? This will also be theta. This is also theta. So specifying only theta will not help you to reach your particular point. This is the particular point that you have to locate. So if you are specifying theta, you are closer to approaching that point, but there will be so many points on the surface of the sphere which will obey, or which will be corresponding to this angle theta. Because if you are looking at this cone, see, there is a cone on the surface of the sphere. There is a cone inside the sphere, and this is a circular edge of the cone, and the circular edge of the cone will be over the surface of the sphere, and any point over the circular edge of the cone will be corresponding to an angle theta. Therefore theta, it is good thing to measure theta. It is good thing to specify theta. We are very closer to the location, but still that is not enough to locate the point, because we have many points which corresponds to theta. Now, how we can specify which is that particular r we are talking about? There are so many r's in this cone which will be corresponding to an angle theta, and we have to tell particularly which r is corresponding to the location that we are going specifically. So in order to find that particular r vector, corresponding to the point that we are going to specify or we are going to locate, what we are going to do is we are going to take the projection of this r vector over the xy plane. Xy plane is here. This is the xy plane. See, this is the x-axis. This was the x-axis. We already know the x-axis, and y-axis is perpendicular to the plane of the paper, and this is the xy plane, and over the xy plane there will be a projection r, projection of the vector r, and we have to see where is that projection, and maybe the projection r is somewhere here. This is a projection of this vector. See, this is a projection of this vector, and we have to check at which angle this projection is from the x-axis, and this angle is phi. So phi is actually the angle between the x-axis. Actually, when I say x-axis, it is the positive x-axis. Okay, the angle between the positive x-axis and the projection of the r vector in the xy plane, and that is phi. That is phi. And when we are specifying that phi corresponds to the particular r vector corresponding to the location that we are looking for. So once we specify phi, we are very clear about the r corresponding to the particular location. See, we first started with r. R is the distance of the point from the origin of the coordinate system, and it can be anywhere over the surface of the sphere. Then we went for theta. Theta is the angle between r and the positive z axis, but there will be many points on the surface of the sphere which corresponds to theta, because if you are constructing a cone, then the corresponds to the angle theta. Any point on the circular edge of the cone, that cone will be corresponding to the particular angle theta. So we are closer to the location, but still we are not in the specific location. And in order to specify the particular location, what we are going to do is we are going to take a projection of r over the xy plane. To take the projection of the r over the xy plane, what you can do is you shine a torch. You shine a torch from the z axis. From the top you shine a torch on the xy plane, then you will get the projection of the r vector of the xy plane, and then look for where the projection falls. If the projection is falling at an angle phi from the positive x-axis, that phi you can specify. Once you specify the phi, then it is all clear that phi will be corresponding to the particular r that we are looking for, and r theta and phi will specifically point a location in the space, and this is called the polar coordinates. R theta and phi are called polar coordinates. You can look what are the possible values of r theta and phi. R can have any value because the point can be anywhere over the space, right? R can have any value. And what about the value of theta? Theta actually is the angle from the positive z axis, and it can vary from 0 to 180 degree, because any cone over this surface can be specified by an angle ranging from 0 to 180 degree. This cone, for example, we have drawn a cone here that is about 45 degree. This theta is about 45 degree, right? This is 45 degree. And if you are coming from here, if you are considering this cone, see, this is another cone, then again the theta is greater, maybe something like 60 degree. And when we are reaching the xy plane, the cone is like a circle. The cone is like a circle. At that time theta is equal to 90 degree. When we are going down, the cone will be like this, right? Then theta will be more than 90 degree, because we have to measure from the plus z direction. More than 90 degree, that is something like 135 degree. For example, this angle is 135 degree, and we are going closer like this, and it will be again something like 170 degree, this angle from the positive z axis 170 degree. And when we are reaching here, then it will in the minus z direction, then the cone will become a line. So in the plus z direction and the minus z direction, the cone will be like a line, and in the plus z direction the cone will be an angle of 0. Here the cone will be an angle of 0, and here the cone will be at an angle of 180 degree. That is a maximum possible. So theta can vary from 0 to 180 degree, or in other words, it can vary from 0 to pi. And what about phi? Phi actually is the projection of the r vector over the xy plane. This is xy plane. For example, this is xy plane, this x-axis, and this is y-axis, x and y-axis, and the projection of r vector can fall anywhere over the x-axis, right? It can fall here, or it can fall here, fall here, fall here, fall here, fall here, fall here, anywhere. It means that it can fall at an angle of 0 to 360 degree, 0 to 360 degree. If it is falling here, that is something like 45 degree. If it is falling here, that is 90 degree, and if it is more than that, then it is something like 135 degree. If it is reaching here, it is 180 degree, and if it is something here, it is something like 190 degree or 200 degree, and like that. It can come up to here. If it is falling back to here, then it is 360 degree. 360 degree and 0 degree, they are making only similar sense. So it can vary from 0 to 360 degree, or it can vary from 0 to 2 pi. So phi can vary from 0 to 360 degree or 0 to 2 pi, and theta can vary from 0 to pi. And you have to remember, in the xy plane, theta is equal to, in the xy plane, theta is equal to 90 degree, right? Theta is equal to 90 degree in the xy plane. In the positive z axis, positive plus z axis, theta is equal to 0 degree, and the minus z axis, theta is equal to 180 degree, right? So this is how we are locating a point in terms of polar coordinates. And there is a relation between the polar coordinates and Cartesian coordinates. The relation is very simple. The relation is z is equal to r cos theta, x is equal to r sin theta cos phi, and y is equal to r sin theta sin phi. So these are the relation between the Cartesian coordinates and polar coordinates. If you have r, theta and phi, you can convert them to the Cartesian coordinates x, y and z using their relations. Okay, so these are the polar coordinates. You already know now what are polar coordinates, and with this basic understanding we have to move on to study particle in a ring. So in the case of the particle in a ring, we suppose that the ring is in the xy plane. A ring is in the xy plane. This is xy plane. Actually, this ring is in the xy plane. This is the xy plane, and the particle is moving. It's a microscopic particle, and this microscopic particle is rotating through a ring, or it is rotating in a circular fashion or circular way or circular path. And this is the origin. And the distance from the origin to the particle is r. This is the distance. This is r. And this particle is not under the influence of any external force. It's a hypothetical system. It is making a circular motion. Still, it is not under the influence of any external force. Since it is not under the influence of any external force, the potential energy is equal to 0. So this is a hypothetical system even if it is a hypothetical system, why we are going to learn this is because it is very useful in order to understand the real systems. We will extend these results, the results that we are going to get from this quantum mechanical system, we are going to extend these results to the real system. So we should have some basic understanding about this kind of simple systems. We already learned the simple systems like a particle in a one-dimensional box and three-dimensional box and many variants of that, and this is also a simple system. In that case also we consider that in the particle in a box and the potential energy is zero, means the particle is not under the influence of any external force. Here also the particle is not under the influence of any external force. So this is a hypothetical system, but it is a simple system, but the results that we are going to get from this simple system will be very useful to treat the real systems. That's why we are going to learn this. So the particle is moving through the ring at a radius r, and you know how to treat the system, because in the previous semester itself I have taught you, when you are going to deal with any quantum mechanical system, what you have to do is you have to make the Schrodinger wave equation. The Schrodinger wave equation is h cap psi is equal to E psi, where h cap is the Hamiltonian operator, that is the total energy operator. Psi is the wave function corresponding to that particle, the moving particle, and E is the energy. Psi is again the wave function corresponding to that moving particle or microscopic particle, and that wave function is the state function that is going to explain the state of that system. And here we are going to consider the particle in a ring in the xy plane. Okay, so the Hamiltonian in this case, h cap is the total energy operator. As you know, h cap is equal to minus h square divided by 8 pi square m del square, right? This is a Hamiltonian. Minus h square divided by 8 pi square m del square, that is minus h square divided by 8 pi square m del square is dou square by dou x square plus dou square by dou y square plus dou square by dou z square, right? Since our particle is in the xy plane, we don't need to worry about this one, so we can omit that part. So h cap is equal to minus h square divided by 8 pi square m dou square by dou x square plus dou square by dou y square. That is a Hamiltonian in our case. But I said already that we are not going to deal this system in terms of Cartesian coordinates x and y. We are going to deal this system in terms of polar coordinates r, theta and phi. Therefore we have to apply the Hamiltonian in terms of the polar coordinates. In terms of polar coordinate, the Hamiltonian, we have to set up the Hamiltonian as del square in terms of polar coordinates is 1 by r square dou by dou r of r square dou by dou r plus 1 by r square sine theta dou by dou theta of sine theta dou by dou theta plus 1 by r square sine square theta dou square by dou phi square. That is the del square in terms of polar coordinates. And here our particle is in the xy plane. In the xy plane theta is equal to 90 degree. We already learned that in the xy plane theta is equal to 90 degree, and so theta is a constant. In our case it's 90 degree, and in our case r is also a constant because the particle is rotating in a ring of constant radius r. So theta and r are constants in our case, the particle. So we have to see that since theta and r are constants, the derivatives with respect to r and theta, these terms can be omitted. means first terms here, this is dou by dou r of something, here is dou by dou theta of something. So these two terms can be omitted. So in our case, the only part remaining is 1 by r square sine square theta dou square by dou phi square. This part only will be remaining in our case. Therefore h cap in our case is h cap is equal to minus h square divided by 8 pi square m 1 by r square sine square theta dou square divided by dou phi square. But sine square theta, actually sine theta is equal to 90 degree in the xy plane, 90 degree. Therefore sine theta is equal to 1. Therefore sine square theta is equal to 1. Sine square theta is equal to 1. That is equal to 1. So what we have here is h cap is equal to minus h square divided by 8 pi square m r square dou square divided by dou phi square. That is our Hamiltonian. Minus h square divided by 8 pi square m r square dou square by dou phi square. And here m into r square. M is the mass of this particle and r is the radius of the circular path of that particle, and therefore mr square is equal to the moment of inertia I. So we can substitute mr square with I. Therefore we have h cap is equal to minus h square divided by 8 pi square I dou square divided by dou phi square. So now we have the Hamiltonian here, and we are going to apply, we are going to set up the Schrodinger wave equation for this system. Let us suppose that since our variable here is phi is the variable here, so let us say that in our case the wave function is f of phi. F of phi means f is the wave function and that's a function of phi. Okay, f of phi is the wave function. Therefore our Schrodinger wave equation is h cap f of phi is equal to E f of I. This is our Schrodinger wave equation. And we have to solve this Schrodinger wave equation. H cap f of I is equal to E f I. Well, in simple terms we can write H cap f is equal to E f, because f, wherever I write f, you have to remember that f means that f of I. F means f of I. Just to simplify, I write f. Okay, this is the Schrodinger wave equation, and now we have to solve this Schrodinger wave equation. So the Schrodinger wave equation is our Schrodinger wave equation is h cap f of I f is equal to E f, and therefore minus h square divided by 8 pi square I d square f by d phi square is equal to E f. So this is a Schrodinger equation. See, this was h cap is already given here. H cap is equal to minus h square divided by 8 pi square I dou square by dou phi square. We don't need to use the sign dou anymore because we have only one variable here, phi. Therefore we can use d square f by d phi square, that is equal to E f. Okay, now we can simplify this equation. What I am going to do is I am going to cross multiply this part to the other side of the equation. So I get d square f divided by d phi square is equal to minus 8 pi square I e divided by h square into f. Let me take minus h square I e by h square as not minus, without a minus, let me take this as m square, then I get d square f divided by d phi square is equal to minus m square f minus m square f, where m square is equal to 8 pi square I e divided by h square. So if I am bringing this minus m square f to the left hand side, I get d square f by d phi square plus m square f is equal to 0. This is a simple differential equation, right? Second order simple differential equation, d square f divided by d phi square plus m square f is equal to 0. You are already familiar with this type of equation. When you learn the particle in a one-dimensional box, you have seen this type of an equation. You remember that d square psi by dx square plus k square psi is equal to 0. You remember that equation when you learned particle in a one-dimensional box in the previous semester. So we have obtained a similar equation here. So you already know the solutions of this equation, that the solutions are d square f d phi square plus m square f is equal to 0. So solutions are f, that is f is equal to n sine m phi, that is a solution, or f dash is equal to n dash cos m phi, and these are the real solutions. And we have an imaginary set also. The imaginary set is f double dash is equal to a exponential plus or minus I m phi.